Okay, we are going to start our afternoon session with Olalla Castro Alvaredo from the University of London, and she's going to speak about out of equilibrium dynamics of integrable models in the presence of unstable particles.
Yeah, thank you. Thanks a lot. Thank you to everyone for being here and at home, and to the organizers for inviting me, especially Thibaut. So I'm very happy to be here. I'm going to be talking about something that has really nothing to do with climate change, what came before, so something quite different, and probably quite far from what many of you do. So most of my talk, I think, is going to be introduction to the basic ideas, and then maybe if I have time, I'll show you a couple of videos towards the end. So this is work about out of equilibrium dynamics, which is certainly part of the topics discussed here, and there's certain integrability because the model I'm looking at is an integrable one. And there is some hydrodynamics because the method we used to do our numerics and to look at the dynamics is based on hydrodynamic equations, what we call GHD nowadays. So, okay, let me start by telling you that the work, what I'm going to talk about very quickly, just half hour, is really a mix of things that we've done over several years and in several papers. So there are 3 papers and 1 recent preprint. So these are things you can look at after if you're interested in this. And these are all the nice collaborators that have been involved in that work, one of which is Benjamin, who is here, and we'll talk later this week. And the others are, well, Pasquale Calabrese and several postdocs, well, Francesco is not postdoc, another professor, several students and postdocs. The structure essentially consists of 3 parts. So the first part is to tell you something about a model you probably haven't never heard of. It's a little bit exotic to lots of people, but still an integrable model with a diagonal scattering matrix. So if you know about integrability, you would understand at least what I'm talking about. Quantum integrability, so quantum field theory is what I'm talking about. And this model is part of a family. They are called homogeneous sign-Gordon models. These were studied by a group of people at the University of Santiago de Compostela in Spain, where I did my PhD. And they classified their properties, they wrote the scattering matrices, so they did lots of things in the 90s. And one property these models have, which is special, is that although they are integrable, they also contain unstable excitations in the spectrum. So I will explain what that means. But the fact that these unstable excitations are there means that there is usually one or several free parameters in the scattering matrix. And by varying those parameters, different regimes of the model can be visited, different energy regimes. And one of the features that are found for these and more complicated models is that if you look, for example, at the flow of the C function or some RG function that you can compute, for example, from thermodynamic ansatz or Samolov-Zhukov C theorem, what you see is this function, it flows, well, at low energies, 0, and for very high energies in the UV, so beta is inverse temperature, it flows to a higher value, the ultraviolet central charge of the underlying conformal field theory, but in between it can visit other RG fixed points. So for example, this model, it visits 2. There is one plateau at central charge 1, and then a later plateau at central charge 6/5. So depending on the temperature at equilibrium, we're talking now, we have this flow visiting nearby or coming close to different RG fixed points. So this model, like many integrable models, can be described using hydrodynamic techniques. And in particular, something that we were aiming to do when we started this project was to explore how the presence of these unstable excitations and these free parameters affects the hydrodynamics. So that's what we essentially did, looking at different quantities. So in my talk, we'll look at those things, introduce the model, introduce the hydro, and then show you some results. So let me tell you a bit more about the model. So this particular one, the SU3 level 2, the name refers to Wessel-Minowitten models, if you're familiar with this. It doesn't matter. The important thing is that this is a model that has 2 stable particles in the spectrum. So it's a simple scattering matrix. It's a diagonal scattering matrix, meaning that these 2 particles scatter and the exact same particles come out of the scattering, and that's all that can happen. So usually, because there are just 2, I label those particles as plus and minus. It's just a choice of names, okay? There is an underlying algebraic structure which is actually not so important today given the short time, but these models are connected to actually total quantum field theory, and so they have a very rich underlying algebraic structure behind. So the labeling of particles has something to do with that algebraic structure. Never mind, what's important is that we have essentially two possible scattering processes here. Either a particle scatters with itself, so plus with plus or minus with minus. And in that case, they behave as if they were two free fermions. So their scattering is just -1. So this is like a free theory. But if they scatter with each other, something non-trivial happens, and the scattering matrix is this one here. And that's where this free parameter sigma enters. Okay? Now, the idea that there is an unstable particle in the model is related to the fact that this scattering matrix has a pole, which is not in what we call the physical sheet, which would be imaginary parts of theta between 0 and pi, but it has a pole which has a real part sigma and imaginary part I pi half. And according to Breit-Bigness formula, that can be interpreted as an unstable particle being formed. Okay? So there are a few more equations here about that. This here is the logarithmic derivative of this S matrix, and I'm writing it now because this is the sort of function that enters the thermodynamic Bethe-Ansatz equations later on. So this phi, which we call the kernel, is going to appear later in some equations. And as you can see, the variable theta, which is, by the way, the rapidity, so it's related to energy and momentum in one dimension, is shifted by this parameter sigma again from the S matrix. So there are two regimes that one can see, which I referred to already. So when sigma is very large, this S matrix actually goes to 1, and what we have is just two free fermions. And that's what we were seeing central charge equals 1 at low energies. These are these two free fermions. But if sigma is large enough, there is this unstable particle, and if you use Breit-Bigness formula, you can compute the mass and the decay width of this particle, and they both scale with the exponential of sigma half. So this sigma half becomes an energy scale, which is very relevant in this problem. It keeps popping up in lots of places, and what you often find is that functions change their behavior when the energy is comparable to that scale of sigma half. So here are the kernels. So you see that they are shifted by sigma. So for sigma 20, they are very, very peaked, as they usually are in the TBA, but they are peaked at a rapidity that is not 0. So in particular, they are mirror reflections of each other. So they are parity related to each other, the quantities for these two particles. So, okay, these are details that, I mean, I shouldn't go into because I don't have a lot of time. Sense in which. So what's important? Right. I hope it's not mine. Okay. Let's do that, including mine. Okay, so let's go on. So something I was going to say is that, so at this stage, so we have these two stable particles, and in integrable models, in integrable quantum field theory, everything we talk about always refers to the stable particles, to the asymptotic particles. So when I compute things later on, it's always going to be for this plus or this minus particle, often for the plus, because the minus is related to the plus by some parity transformation. So you might ask, in which sense can I talk about things related to unstable particles? Well, I can do that because you will see that when I look at quantities for the stable excitations, they are going to have new features, which is possible to interpret as indicating the formation of this unstable particle. So this is what we're going to explore, and we're going to explore that out of equilibrium in a particular situation. So to do that, we're going to use something called generalized hydrodynamics. So hydrodynamics, we heard about a little bit this morning, but since I'm one of the first speakers in the conference, we haven't heard much about this. We're going to hear more about it, I think, even in the next talk, probably. So the idea of generalized hydrodynamics, many of you might be familiar with this, but it is hydrodynamics still. So the concept is still to describe things using this idea of fluid cells, and the idea that if we have a macroscopic system, instead of trying to describe it macroscopically or microscopically, so every single atom, we might want to go to an intermediate scale, the mesoscopic scale, where we can talk about fluid cells. And fluid cells are entities which are big enough for them to thermalize independently to some distribution, but they are much smaller than the whole system. Okay. Now, this approach can be applied to quantum field theory as well, as it turns out very efficiently, and to integrable models. And you will probably be familiar with the idea that has been developed a lot in recent years, that for integrable models, something special happens, namely that what happens in fluid cells is that eventually there is some sort of thermalization, but not the standard one. So there is no thermalization to a Gibbs ensemble, which is what would happen for a generic model. But instead, if we follow the principle of local entropy maximization, what happens in integrable models is that they seem to equilibrate. They equilibrate to something which is called a generalized Gibbs ensemble. So something that involves all the conserved quantities of the theory, both local and quasi-local. So this is something that's been studied now for quite a few years, very successfully. And generalized hydrodynamics is essentially the theory that follows from this realization. So you can develop a hydrodynamic theory that now takes into account this idea, the fact that independent fluid cells do not thermalize, but they do equilibrate to generalized Gibbs ensembles. Okay, so there are two papers, one of which I was part of in 2016, where this was developed into an efficient theory to compute things. In particular, a theory where you could compute the currents and then the average currents and densities associated to those conserved quantities in this equilibrated state at long times. So I'm going to tell you some of the equations that emerge from this theory quite quickly. So the first input that enters into this generalized hydrodynamic theory is a quasi-particle description of the excitations. Okay, so in integral models, we're very fortunate because we have this quasi-particle description as part of the toolbox of integrability in a way. And this comes from something called the thermodynamic beta-ansatz or the beta-ansatz description of systems at finite temperature or in GGEs in general. So I'm going to remind you of the sort of equations that come up in here. So if you have a single particle, so just so we don't have lots of indices, the traditional equation you start from in the TBA is an equation that looks like this. And there are several things in there I have highlighted. So this is for single particle, that's why there are no indices. Now this symbol represents a convolution, so there is an integration that is involved in there. These are nonlinear integral equations in general. This is this kernel, this is this phi, which was the logarithmic derivative of the scattering matrix. This L function depends on whether the theory is bosonic or fermionic in one dimension. So for fermionic theories, meaning scattering matrix of rapidity 0 is -1, the L function is a nonlinear function of this epsilon. Okay, and the epsilon is called the pseudo energy. So it's a kind of generalization of energy in the presence of interactions. And what's special for GGE is that this term here does not just involve the energy, which is what happens in a Gibbs ensemble, but it involves all the one particle eigenvalues of all the conserved quantities. Here are some examples. So for relativistic QFT, the particle number, for example, eigenvalue would be 1, the energy would be cos theta if the mass is 1, momentum would be sinh theta if the mass is 1, and so on. So you have all this tau of conserved quantities. And there is one operation that one uses very frequently in this context, which is this dressing operation. So if you take the derivative of this equation with respect to one of these betas, what you get is another equation that you can write like this. And this is an equation where you have here the one particle eigenvalue of some quantity. Here you have another convolution involving this function, the dressed version of that quantity. And this n that comes out in there, this is the occupation number, what we call this the occupation number or filling fraction for fermionic distribution. So it's a function again of these pseudo energies there. Now, if you use principles of hydrodynamics and put that together with these equations, what you find is that actually this m function, this occupation number, becomes something which is sometimes called the normal modes of the fluid description. Namely, this function satisfies this continuity equation like this, like you would find, like we saw earlier, actually, in your talk, but with something here instead of 0. But at the Euler hydrodynamics, that's what it looks like. And then here there is a function which is called the effective velocity of these modes, of these quasiparticles. The effective velocity itself is also a function of dressed quantities. It can be written as derivative of energy over derivative of momentum dressed according to this equation. Now, if we have already equilibrated, normally or often these quantities here, they're all just functions of theta and nothing else. But if you are in an out of equilibrium situation or a dynamical situation, in general, things can depend on position and time as well. And this is what's going to happen in my example when we go out of equilibrium. But in essence, if you can numerically solve these equations, you can compute everything which is important to describe this quantum system. Okay, so let's try and do that. I mean, one thing that you can compute, for example, which is actually, it was the key result from our original paper, was, for example, the current, the average current and the average density associated to a particular conserved quantity. They're given by these formulas. And at the time, the formula for the densities was, I think, a simple generalization of something that people knew, but the currents was actually non-trivial, and it was something that appeared in those papers first. I'm not going to discuss those today. Here I have a picture of what this effective velocity means. So it just means, well, it's an effective velocity. So these quasiparticles, as they interact with each other, they don't propagate just as if they were free, but their velocity somehow gets, average velocity gets altered by all these collisions, and it becomes something called an effective velocity. If the theory is free, a quantum field theory, relativistic, this function is just cosh over sinh, so sinh over cosh, so it's just tanh. But if the theory is interacting, this gets slightly deformed, or very deformed if the theory is quite exotic. So in my talk, I'm going to show you pictures actually of just really these two functions in the time I have left. So this function here is called the spectral particle density, or the density of occupied states from the TBA. So some of you will be familiar with that. So that, actually, there should be an X and T here as well. But so you can write that as energy dressed times this occupation function. And if you integrate this function over rapidities, you get particle density, which is a very physical quantity. And we're going to be looking at something related to this, okay, later on. So, okay, so now we have the tools. So let's compute something with this. So let's go out of equilibrium. So to go out of equilibrium, we can go out of equilibrium in many ways. But what we wanted to do in our work was to find the best way to emphasize the properties of these unstable particles. And what can unstable particles do? Well, they can be formed if there is enough energy, and they can also decay. So we want to see if we can see signatures of those behaviors. So one way we thought of doing this, which turned out to be quite successful, was to create an out of equilibrium situation by starting with an initial state described by this temperature profile. So what does it mean? It means that at time zero, we're going to take our homogeneous Gordon model, and we're going to initialize the model with a temperature that is a function of position. It's a function of x, but not of time. So essentially, for every value of position, we have a Gibson sample, okay, at the beginning, but a different one for every x. And in particular, we chose this profile, which is Gaussian, with some characteristic temperatures, Tm and Ta. So Ta is the asymptotic temperature, or temperature of the bath that we call. So if we're very far from the center, we have that residual temperature, which could be 0, for example, or not, but is lower. And then in the middle, we chose to put our highest temperature. The idea is that the temperature we've put in here in the middle, we choose it so that it's large compared to the mass of these unstable particles. So hopefully many of them will be formed around x0. And then as we let time pass, essentially we are releasing this hot matter, these particles, into a cold environment. And what they're going to do in particular is they're going to decay. Okay, you would expect that when they don't have enough energy to sustain the binding. So this is going to happen, and we're going to see some signatures of it. Okay, so decay under time evolution. And we're going to also see that turns out that the presence or absence of the bath has an effect on some phenomena that we can also look at. Okay, well, this kind of problem can also be solved in a more analytic sense. There's an analytic solution, but really, essentially, at the end of the day, one has to solve these equations numerically. The approach to do that is already explained in this paper, actually, But in our work, we used a method that's a bit, let's say, perhaps more general or more appropriate to treat all sorts of non-equilibrium situations, which is a code in MATLAB that was written by Friedrich Müller, and is actually freely available online. It's called the iFluid package. So this is a package that allows you to solve these equations for any initial conditions you like, and also generalized versions of them. So you can introduce viscosity, other phenomena as well. So it's a nice package, but somehow for us probably too general for what we needed. Okay, right. So let's look at a couple of features, and then let's end with some videos looking at what happens out of equilibrium. So before we look at out of equilibrium, perhaps it's useful to look at equilibrium, just to see that actually for this model, because of its peculiarities, already at equilibrium one sees things that are a bit different from the ordinary. So this is a picture of this rho p function, this particle spectral density function at equilibrium. So now it's just a function of theta, rho of theta. And for a free fermion, just to give you an idea, for a free fermion, this function normally looks like this. So there are two peaks, and these peaks are actually centered around some values of theta, which are related to temperature. So this is essentially log beta half minus log beta half, or vice versa. Okay, and one can work that out just from the definition of all these functions. It's a simple thing to prove. Now, if you look at a particle plus in our model, you see that some features are similar. So you still have these two peaks at about the same places at equilibrium, but you see that they are not the same height, and there's an additional one. Okay. Now, one of them, in fact, is exactly the same as for a free fermion. And the reason for that is actually this picture of the kernels I showed you a few slides ago. So remember the kernels, the phi function was picked around some value of theta, which was essentially sigma or minus sigma. And what that gives for this model is that essentially for the other value of theta, in this case theta positive, all the functions for particle plus, they look just like for free fermion functions, because the kernel is zero there, essentially. So it's as if they were free. But if you look at theta negative, there is now interaction, and so this function changes. Now this peak gets higher, we call this interacting peak, and there's this little peak that gets formed, and the position of it is actually related to the value of sigma, okay? So there's a lot of analysis in our papers I cannot fully repeat, but just to tell you that the extra area of this peak compared to this one and the area of this one are about the same, okay? And one can actually argue, if you put together this with the same picture for particle minus, which is essentially flipped over, that this extra rho, which is essentially an extra energy density, when you integrate it, you can associate that with unstable particles, with a density of unstable particles. So in a way, these are particles of type plus, which are interacting with particles of type minus and binding to form these unstable particles, okay? So there are many ways you can reason that. This picture is not enough, but there's more evidence in our papers. So that's what we have at equilibrium, at some temperature, Tm, okay. Now, if we expand this to our initial condition, so our initial condition was a Gaussian of temperatures. So if we now plot this at time 0 with our initial condition, we have here the same picture I just showed you, but with color-coded. So essentially, if you cut it across at x0, you would see again the three peaks, just as I show you. And then if you go a little bit away from x, you still see three peaks. And well, as you go further and further, you see less and less, because in this case, the temperature of the bath is 0. Okay? So you have these peaks localized in there. And in fact, if you look at the effective temperature, which I didn't talk about, you see this in the initial conditions. So the effective temperature, essentially, most of the time, is pretty much like a tanh theta. So it's either +1 or -1. This is what the red and blue represent, value 1 and value -1, which is what you have for a free particle. But then there is some kind of transition area region. And then around here, which is where this little peak of the unstable particles is, this effective temperature gets shifted. This function gets sort of shifted, okay? So it's not a tanh shape around θ0, it's a tanh shape around some other value of theta, which is related to the sigma again. So this is still initial condition, equilibrium. Now what happens out of equilibrium? Since I have 5 minutes, I think, I'm gonna go straight to animations, which are, I think, actually gives you the whole message with less slides. So this is a video, an animation that one of my students did, or my two students did, Cecilia and Alexandra, that puts together all of this. So here we have our 3 peaks again, but now they're going to start moving in time, okay, because we have some dynamics in there. And these 2 examples show you what happens when the temperature of the bath is 0, okay, and when the temperature of the bath is not 0 but is low, okay. If you look here before anything moves, you see the 3 peaks, and here when there is a bath, you see some additional ridges. This is a bit lighter blue, hopefully you see. So you have 2 little mountains in there, which is due to this low temperature of the bath, which is like a pre-particle in there, superimposed. Now, if you make this move, you'll see that actually, if you follow this little peak, so this density of unstable particles, 2 different things happen depending on whether the bath is there or not. Okay, so let's see if this plays, hopefully. Oh, no, what happened? Yeah, there it is. Okay, so they start moving, right? Yeah, and stop it there before I go on YouTube suggestions. So they start moving, and you see that in the case when there is no bath, what actually happens is that this little peak just dissolves and it leaves a tail. So you have a tail in there that's lighter. You have a tail of slower particles that get just kind of decouple and stay behind. On the other hand, when you have a bath, you see that there is a finite density of these particles that survives in the long term. And you can keep doing this simulation for very long times, and you see this residual density staying. It seems like this little peak is riding on top of this ridge, on top of this bath, okay? Now, that is really essentially what it's doing, okay? So the presence of the bath helps this residual density of unstable particles survive in the long term. And because they survive in the long term, one can show that they actually have some effect on the behavior of thermalized quantities. There are still some unstable particles there, even after a long time, okay? I can show you the thing again quickly. Oh, no, sorry. So you can see my tastes. Not really, I haven't seen all the stuff, I swear. Okay, so that's probably enough, yeah. Yeah, so, well, here is, in my previous slide I didn't show, but I had another video here which was actually to show why this little peak survives on top of the bath. So there's some sort of magnetic effect in there. That little peak surviving, it survives because there is, if you look at the density of particles of the other type, of type minus, there's actually a very high density of particles of type minus in the same region of space, in a way, as this little peak. And so these other particles are interacting with the pluses there, and they are dragging them, essentially, at their own speed. And they're able to drag them because there is this kind of bath that is in there. So they're being carried, a little bit like happens with a magnet. Okay, so if you have something that has magnetic properties and you pass a magnet by it, somehow it follows the magnet. Okay, so these particles of type plus, they kind of follow the particles of type minus, and so they go faster than they were expected to go, in a way, and they survive in the long term. Okay, they're being dragged. Okay, so yeah, I know I have to finish. So at least I show you this. Let me just tell you something that, well, that decay of this little peak, in the first case, is something that can be quantified. Turns out that is universal, so that's something we studied in detail in a later paper. And then what we did in our most recent paper was actually to look at entropy in the stationary state. So when you do a quench similar to this, not necessarily this, but something similar, and you look at what happens after a long time at the entropy, there are actually 2 things you could look at. There is some result by Calabrese and Cardi that tells you that the entropy is going to, for large times, is going to have some doubly linear behavior. So it's going to grow linearly with time, up to a certain time related to the temperature of propagation, to the velocity of propagation of these quasiparticles, and then it saturates to some value which depends on the length of the system. So if you compute, essentially there are 2 functions here, R and P, which are model dependent, and you can try and compute those. So one of them tells you entropy per unit length, density of entropy in the stationary state. The other, the R, is telling you the rate of change or the rate of growth of entropy if it's growing. Okay, so these are two things we looked at in this context after a quench, and I just have two pictures and then I'm done. So these are two pictures from our recent preprint. So the two pictures essentially reflect how these unstable particles have an impact on the behavior of these two quantities. So here, this is the entropy per unit length, but it's normalized by its maximum value so that many curves can collapse into each other. What's important here is that there are actually two different behaviors, two plateaus. They depend on, and these depend essentially on the energy scale. So essentially, for it doesn't matter what this kappa is, but for kappa less than 0, there are no unstable particles. For kappa bigger than 0, energy of the quench is enough to form these unstable particles. And so the density of entropy increases a lot. It increases with the number of degrees of freedom. And in fact, even this plateau can be predicted. This actually is the ratio of the central charges of the two UV fixed points. And another thing that you see if you look at the rate of change of entropy is that actually also around the place where the unstable particles are formed, in terms of this sigma, there's a depletion. There's a depletion of this rate of change and then growth again. Now, that is a phenomenon that has been observed in other situations as well. Some people have called this the dynamical Gibbs paradox. It's something we're still trying to understand physically, understand better. But one can really certainly see it for our model. Okay, so let me just conclude. So GHD, generalized hydrodynamics, can offer some new insights into scattering, decay, and formation of particles, which is something that is not commonly studied in integrability because there are very few examples of integrable models that have these unstable particles. So this is a model where we can study this. Well, we see signatures of the formation and decay of these particles, and some of those are, for example, additional maxima of the spectral density, additional plateaus of these effective velocities. There's a local minimum of the entropy growth rate I just mentioned. There are some universal features that one can find. This I didn't have time to explain, but one can actually, when you see this tail of particles remaining after a long time when there's no bath, there is a decay rate for that peak one can study, and turns out that there's an exponential decay with a decay rate that's also universal. And yeah, for generic quenches, there seems to be a finite density of unstable particles that survive in the long term. And so even if the particles themselves have short lifetimes, and they do for sigma large, somehow they are being created all the time to preserve a certain density for large times, even sort of after equilibration, it seems. So that's it. Thanks a lot. That's my talk.
Thank you very much. We are a bit out of time, so I suggest just one short question. Yeah. If there is. Yes.
Are there any connections with the classical limit Stein-Gordon equation, like dispersive hydrodynamics?
Classical limit of Stein-Gordon. Well, not that I know of. I don't know. So although the models are, misleadingly called homogeneous Stein-Gordon, they don't really have much to do with Stein-Gordon. They're all diagonal. So the underlying classical theory is not like Stein-Gordon. It's more like Toda, and Toda. So I don't know. I mean, I don't see a direct link to that, even though both are integrable, of course. But yeah, somehow Stein-Gordon has a lot more structure, the breathers, and it's more interesting in that way.
Okay, thank you very much.
Thanks.
I can ask you to stop sharing your screen.